today we will study a very powerful tool which is called the Uniform Boundedness Principle. But to state it and to prove it, we need some preparation. We will start with the Baire category theorem. Before I state it, let me recall the notion of density, which we considered, well, a couple of months ago. So let us make a short recap. So let us first, for this recap, fix a metric space. And recall that we called a set dense in the other set if B is contained in the closure of A. So one set is dense in the other set. The second definition to recall is that a set is called everywhere dense if its closure coincides with the whole space. The third part of this definition, we say that a set is nowhere dense if its closure does not contain any ball. And after this recap, we are ready to go to the Baire's category theorem. So let X be a complete metric space. And we also want that the set X is non-empty. So let X be non-empty and let X rho be a complete metric space. And also let us consider a collection of closed subsets of the set X. So the statement of the theorem asserts that if a union of these sets contains an open ball, then at least one of these sets contains this open ball. So first of all, I will write down a contrapositive of this statement. The equivalent statement would be that I will take the negation of both of these and swap them. So the equivalent statement will be if none of these sets AI contains an open ball, then neither do the union. The union of all of them does not contain an open ball as well. Suppose to the contrary, that the union of all AIs contain an open ball, but all of the AIs are nowhere dense. Hence, inside this open ball, we can find a closed ball of smaller size, say centered at the point A and of radius epsilon. Let this ball be a subset of the union. Since A1 is nowhere dense, in this closed ball we can find an open ball which does not intersect with AI. Inside of this ball we can find a closed ball, a smaller one, which still does not intersect with A1. A closed ball centered at x1 and of radius say R1 inside this one, such that it still does not intersect A1. And we can suppose that R1 is less than half. In a similar fashion, we can find a closed ball inside this closed ball which does not intersect with A2, using the fact that A2 is nowhere dense. And also we can take R2 to be less than 1/4. Continuing this process, we will get a decreasing sequence of closed balls with ready going to 0. And all the elements of this sequence are inside this closed ball. Since this space X is complete, this sequence of these balls has a non-empty intersection. So this point X belongs to this closed ball, and in particular it belongs to the union of all AIs. On the other hand, by construction, X belongs to this first ball, and hence it does not belong to the first set. Also, X belongs to this closed ball, and so it does not belong to A2. And so on. We conclude that X belongs to neither of AI. And so, it does not belong to the union of all of them. So it does not belong. So we have obtained the contradiction which proves the result. Let us consider the set of rational numbers the set Q, and let's enumerate it as Q1, Q2, and so on. So this set in particular can be written that Q can be written as a union of AI, where AI is a singleton. AI is the single real number, real rational number Qi, and as a singleton it is closed. Now we will go back to our realm of linear operators. The next result for today is the Uniform Boundedness Principle, or UBP for short. So let us consider two nonlinear spaces, and one of them is Banach. And now let us consider a sequence of bounded linear operators from x to y. And let us suppose that this sequence is pointwise bounded. So at every single point of x, this expression is bounded. And from this pointwise boundedness, we want to conclude the uniform boundedness. Let us also remark that this result holds not only for sequences, but for an arbitrary collection of operators. Let's prove the theorem. So suppose that Tn is the family of bounded linear operators from x to y. Such that it is pointwise bounded. Let us introduce specific subsets of X. Sets A, K, which consist of all x's from the space X, such that the norm of Tnx less than or equal to k for every n. So it is easy to see that all of these sets are closed, and also this condition guarantees that the union of all ak equals to x. Which means in particular that the union of all these sets contains an open ball of x. By Baire's category theorem, we conclude that there is, well, at least one of these AK contains an open ball. Let's call it A sub K0 and call the ball somehow as well. Ball centered at x naught and radius r is inside a k sub 0. In particular, this means that this pointwise boundedness holds for any x from this ball. Well, with constant k0. T and x, the norm of this, is less than or equal to k0 for any x from the ball. And well, for any n. What I will do now is I will take an arbitrary element from the space X, from the whole big space, and then I rescale that X in a way that it will belong to this ball. What I will do first, I will write from the right to the left. I will take X and divide it by its norm. Let's also suppose that X is not 0. Now, I will multiply it by R over 2. And now I will add x0 to this one. And I will call it y. And it's not difficult to see that for every x from X, this element y belongs to the ball. Let me now express X in terms of y. Now let me estimate the norm of Tnx. Now I will use the triangle inequality to estimate this norm as a sum of the norms. But both elements x0 and y belongs to the ball. So for them, for the norm of Tn of them, we have this estimate. So this one is less than or equal to 4 times k0 times norm x over r. Hence, the norm of Tn is less than or equal to 4k0 over r, by definition of the norm. And so we have proved that the sequence of norm is bounded. In the theorem, we suppose that X is a complete space, so it is a Banach space. Let me illustrate with the example that this condition is significant. Let X be C00, the set of all bounded sequences, such that there exists n, that xn equals to 0 for every n greater than or equal to capital N. So it consists, the space C00 consists of all sequences with finitely many non-zero terms only. Well, this space is not complete. And let Y be the set of real numbers. Instead of constructing the operators Tn, we will consider the functionals, which are a particular form of the operator. And let Tn of x be the sum of xi from I to n for every x from C00. Well, first of all, it's not difficult to see that all such operators are well defined, and they are, well, clearly linear, and they are bounded. So they are bounded linear functionals of this space. And also, it's not difficult to see that Tn of x, the norm of this expression, is bounded for every x. Because for any x from this space has only finitely many non-zero coordinates. So it's bounded by the sum of that finitely many non-zero coordinates. But the norm of Tn is n, which tends to infinity. So for any n, take the sequence with the first n coordinates being 1, and that will give you this result. So this space is not complete. We have constructed the sequence of functionals. It's pointwise bounded but not uniformly bounded. The uniform boundedness principle is a fairly easy result to state and to prove. However, it is a very powerful result, and we verify the power of this result with the example. Let us consider a space of all polynomials, and we equip this set of all polynomials with the uniform norm on, say, 0 infinity. Is this space complete? If we take a sequence of polynomials, is it guaranteed that the limit of this sequence is a polynomial? No. We know that every continuous function can be approximated by polynomials. So this space is not complete. And moreover, the completion of this space is the space of continuous functions. Well, this is a fairly standard norm, and we quickly figure out that this space of polynomials is not complete. But as we already know, the completeness depends on the norm. So for instance, if we equip this space of polynomials with a very unusual norm, with a very strange norm, let's do this and let's check whether this space is complete or not. Let me clarify what I mean by the set of polynomials. So this set P of all polynomials of a single variable of the form a0 plus a1x plus a2x squared plus so on a dx to the power of a sub dx to the power of d for d in n and a0 ad real numbers. So this is the set of all possible polynomials with real coefficients. And let's equip this set with a norm. So the norm of a polynomial, the maximum of all its coefficients. From the uniform boundedness principle, we know that in a complete norm space, any sequence of operators which is pointwise bounded is uniformly bounded. So if we manage to construct a sequence of operators which is pointwise bounded but not uniformly bounded, the space cannot be complete. And that's what we will do. Let us define a sequence of operators which take the sum of the first n coordinates of a polynomial. Again, instead of operators, we're just considering the functionals. Tn of P equals to a0 plus up to an minus 1. So the first n coefficients of a polynomial. For a polynomial. The linearity is straightforward. Let us prove that this functional is bounded. All these functionals are bounded. The absolute value of this equals to the absolute value of the sum of the first n coefficients. By triangle inequality, I will take the absolute value of each and every of these. Now I can estimate these. So over here we have the sum of first n coefficients of a polynomial. Let me estimate it by the sum of all non-zero coefficients of a polynomial. And the norm of a polynomial is the maximum of all these guys. And there are d of them. So I can estimate it by d times the norm of p. Which tells us that any Tn is a bounded linear operator. Well, by the way, I not just showed that Tn is bounded, I just proved that the sequence Tn of p is pointwise bounded. Let us estimate the norm of the operator Tn. So in the way similar to this one, we can say that the norm of Tn is less than n. Since it sums the first n coefficients of a polynomial, and the norm is the maximum of absolute value of all coefficients. How to prove that the norm is in fact n? Let us take a polynomial which equals to 1 plus x squared up to n minus 1. Then, what is the norm of p? It is 1, but the norm of Tn of p, the absolute value. The absolute value of Tn of p is n. So, the norm of Tn is n, and so the sequence of these functionals Tn is not uniformly bounded. So this sequence is not uniformly bounded, and from the uniform boundedness principle, it follows that the space we consider is not complete. So this uniform boundedness principle, let me say it again, is a powerful tool for checking whether the space is complete or not. Let me finish this lecture with one more result, which is a theorem due to Banach-Steinhaus. I told you that we will see a lot of results due to Stefan Banach in this course, and this is one of them. Let us start with two non-linear spaces, and let X be Banach. Let us also consider a sequence of bounded linear operators such that the pointwise limit exists. So this limit exists for every x. And let us define an operator with the value at the point x being the value of this limit. The assertion of the theorem is that, first of all, T is a bounded linear operator, which shouldn't be surprising for us. We have proved that, we have seen that several times. What is more interesting here is an estimate on the norm of t from above. So it's not guaranteed that the sequence of norms of Tn convergent, but we can estimate the norm of t from above by the lim inf. The proof of this result is an exercise for you. To finish this lecture, I want to discuss this inequality in the assertion of the lemma. So first of all, it is easy to see that there is a sequence of Tn such that in this last line we have equality. So for instance, if we take all Tn to be, say, T1, so we just take a single operator and consider a constant sequence, then, well, the limit exists. The linear operator defined in this way coincides with this single operator from the sequence, and so over here we will get the equality. So I want to show you the example where this inequality is not just not an equality, the values of the left and the right hand side are fairly far from each other. Example. Let us consider a sequence of operators on C0, the space of sequences converging to 0. And the sequence Tn, the operator Tn of x, what it does, it set to 0 the first n coordinates of x. It's not difficult to see that that's the end of the lecture. It's not difficult to see that all of these operators are linear and bounded. Also, it's not difficult to see that the norm of all Tn is 1. So the right-hand side in this inequality is 1. But when we take the operator t being a limit of this Tn of x, we get nothing but 0. Tn is 0, and so, t is 0, and so its norm is 0. And so the left and the right hand side are distant from each other by 1. Well, if you want a huger different distance, multiply Tn by a scalar, and you can get this distance as large as you wish.